Okay, so today we're going to talk about really just some final things that you need in order to do combinational logic in Verilog. We're going to make a multiplexer essentially, and by doing a multiplexer, we're going to illustrate the last kind of handful of concepts. So I'm going to put this, make my tablet fired up, so as I can draw. Give me the page. There we go. All right. Larry asks, so I'm doing everything on a Mac, and for some reason my files are saving. Oh, so RTF is rich text format. It's like if you're using TextEdit on a Mac, that is its version of .txt. I don't know off the top of my head how to make sure it saves those as files. If you use an editor like Visual Studio Code, you won't have that problem anymore. But it's, like I said, RTF is Mac's version of .txt, approximately. Okay. So let's take a look. All right, so let's get into it. Let's make, what do we want to make? Let's make a 4-bit two-to-one multiplexer. Full screen that. Okay. We've already looked in class we've already seen in class how to make a 2-to-1 multiplexer, but let's go ahead and revisit that. Remember that, we want, if we have data inputs A and B, and we have a control input let's just call it C, and then we have an output Y. And we're going to say that Y is a function of A, B, and C, and is equal to A and C prime, or B and C, right? So when C is 0, Y is equal to A. When C is 1, Y is equal to B. And so when we go to draw it, it's pretty simple. It's just 2 AND gates and an OR gate, A and C prime, or B and C. And that's our output Y. And if we were going to make, let's sort of wrap that up and call that a 2-to-1 mux, then what we're going to do, scroll down a little bit, to make it multi-bit is going to be just this. If I'm making, what did we decide, a 4-bit 2-to-1 mux, so I'm going to need 4 2-to-1 muxes, 1 for each bit. So 1, 2, 3, and 4. And I recognize that I'm not doing the correct trapezoid thing. So mux, mux, mux. So let's see, on the input side it'll be let's start at the top, it'll be a 3, B3 and A2 and B2 and A1 and B1 and A0 and B0. And on the output side here we get Y3, Y2, Y1, and Y0. And the last thing we need is our control bits. Remember, for a 4-to-1 mux, we're going to need 2 bits of control. So let's see. How do I want to draw this? Oh, I think I made a mistake. I didn't practice ahead of time. Let's see. 1, 2, 3. Oh, no, it's still 2-to-1 mux. That's stupid. Sorry, in my head I was like, this is a 4-to-1 mux now. No, it's not. It's still just C as the control, and all of them get C as the control. So when C is equal to 0, all of the A's get selected. When C is equal to 1, all of the B's get selected, and they all get passed to Y. So this is what we're going to build. Are there any questions about the structure of what we're putting together? We're going to build one 1-bit 2-to-1 mux module, and then we're going to make a multi-bit version consisting of these separate modules.
Like C1, C9, C0, not C1.
No, it's just each one still runs off the same control, since we're only selecting the individual bits at each place. So it's still just the same thing on each one. It's the same control input for each multiplexer.
Okay.
Yeah, that was I sort of take a minute to be like, wait a second, am I doing this wrong? But no, it's the same C input on each one. Okay, so let's go ahead and let's build it. So I'm in Visual Studio Code. I've got all the other stuff that we had worked on before. So I'm going to create now a module for just our 2-to-1 multiplexer. So mux 2-to-1.v. Module mux 2-to-1, and it's going to have, what did we say, A, B, C, and Y. And our in-module declaration. We got our inputs, we got our outputs, we got our logic circuit. And we're going to do it the easy way, so we don't need any wires. So input A, input B, also input C, and output Y. And we already defined what this is. We're going to say assign Y equals A and not C, or B and C. Just like that. And that's all there is to it. There's our 2-to-1 multiplexer.
Does AND have higher priority than OR?
Yes. So in the order of operations, AND will come first. If you're squeamish about it, you can always wrap those guys in parentheses, and that'll work just fine. So the next thing we need to do is we need to make a test bench for this module. So any module that you write, you need to have a test bench that goes along with it. So let's go ahead and create that. So we'll say mux 2 to 1 underscore testbench tb.v, and let's add our stuff in. Time scale 1 nanosecond, 1 nanosecond. Include mux 2 to 1. Oops, if you use quotes, mux 2 to 1 dot v. Our module declaration 2 to 1 underscore tb semicolon, since there are no input output parameters. End module. All right, so let's do this. We need inputs, we need outputs, we need a unit under test, and we need a simulation. Remember regs for inputs, so reg A, reg B, reg C. Our output wire Y. Our unit under test mux 2 to 1 UT A B C Y semicolon, and then initial begin and end. Okay, well now there's a couple of different ways we could go about it. Let's use the for loop method. We're going to explore some other stuff. So I'm going to call this just variables. Oh, actually, I take it back. I don't need to do that. So in here, I'm going to create a for loop. For, and it turns out I can declare the integer inside. Integer equals 0, I equals 0, I less than 8, I plus plus, begin and end. So what I'm going to do here is I'm going to say the vector, remember A, B, and C. So I'm going to assign all of the values all at once is going to be equal to I, and then we'll delay for 10 nanoseconds. And we could call all of that good. I mean, we still need to add our, let's see, finish, and our waveform stuff. So dump file mux 2 to 1 dot vcd, dump vars 0 mux 2 to 1 tb. I also need a semicolon down here to finish. Let's give ourselves a little bit of room. Let's see. Here's what I want to do. Well, let's run this and let's make sure everything works, and then we're going to add some stuff. So let's do all the same things. I Verilog, option O, mux 2 to 1 dot vvp, mux 2 to 1 underscore tb dot v. No errors, all is well. VVP mux 2 to 1 dot vvp. That ran and everything was fine. And let's take a look. GTK wave mux 2 to 1 dot vcd. So let's open all of our stuff. And let's see. So here in the first one we had A and B, so C is equal to 0, so Y should be whatever A is. So A is 0, Y is 0. That doesn't really tell us a whole lot. Neither does this, because they're both 1. But now let's take a look at it. On the third midterm, A is 0, B is 1, C is 0, so Y should be equal to A, and Y is equal to 0. Then on the next one, A equals 0, B equals 1, C equals 1, so Y should be equal to whatever B is. So Y should be equal to 1, and it is. And we can keep going this way, but as you can see, it's not like you got to really start to think hard at what is the behavior of your circuit when you're looking at the waveform to make sure that it's working properly. So what we want to explore right now is a way to not have to do that by using some if-else structures inside of our test bench. So are there any questions about what we've done so far? This is the basic process. If you're happy with this, you can stop here and move on to the next step. But we're going to take a minor detour to explore some stuff and see if we can't make this a little bit easier. So let's do this. I'm going to say, I want to actually check to see if it's correct based on the logic that I know. So I'm going to say if let's try this. Now I haven't practiced this ahead of time, so this might not work. So if y equals a, and so we're going to look for the cases in which this is wrong. So I'm going to say if y equals a and c equals 1, actually, maybe there's a better way to do this. Let's say, I really should have practiced this ahead of time. Actually, I wonder if we can do this. Y equals our actual expression from before. So let's say A and not C or B and C. And so begin and end. Let's do this. Display test case passes for minterm DI. Now I have no idea if this is going to work actually. Tam, I'm sorry, but that's you're gonna have to talk to Meter Ops Hours or something like that, or talk to Aria or something. I don't know what's causing you to have that. You probably just didn't save your files, and you probably didn't, or you aren't navigated to where your files are. Yeah, that happens if your files don't exist, or if which is to say you haven't saved your files, or if you're not in the correct directory. Those are the two reasons why that happens. All right, so let's kind of recap and say what's happening here. Right? We're going through each minterm using this for loop. We're setting the values of A, B, and C to get the value of I that we want. And then we're going to do a quick check using the same logic expression that we used before. So this should work, but we're going to check and see if Y is equal to that, then that should be a passing test case. So let's kind of take a look and see what happens. Yeah, and naturally some stuff is messed up. Do what everyone does. Go stack.
There are two open parentheses at Y. So we should have one.
Oh, you're totally right. Good catch. Hey, look at that. It's always something simple. You get a gold star. All right. So VVP mux 2:1 dot V VP. Hey, look at that. And test case passes for minterm 0, 1, 2, 3, 4, 5, 6, 7. That's awesome. So now we're actually able to see that everything doesn't work. Let's go ahead and do this. So not equals. Because it doesn't really do us a lot of good to say that everything passes. What we really want to do is see when things fail. So if I say Y is not equal to this, we'll say test case fails for minterm D. Now nothing failed, so that's sort of what we expected. So let's see if we can make it fail. Let's change this. Let's change it to A. Let's do this. And B, and C. And see what happens is so we've intentionally screwed up our logic expression. And look at that. So now it showed the test case fails for min terms 3, 4, 6, and 7. So now we've got a test bench that's a little bit smarter, a test bench that can actually tell us if our stuff is working correctly. So we fix our error, we run it again, and everything is good. No problems. How did he get the VCD and VVP file? I only have mux. You run the Verilog stuff. Like by running the Verilog command, that creates the .vvp file. And when you run VVP, that creates the .vcd file. All right, so any questions about all that weirdness we just did? Okay, so let's do this. So we finished our 2-to-1 mux. Now we want to use that 2-to-1 mux to make a 4-bit 2-to-1 multiplexer. So we're going to create a new module now. We'll call it mux 4-bit .v, just to keep it simple. Now one thing's here, or one important thing, since we're going to use this module, we now need to include it in here. So we're going to go include mux 4-bit .v, since we're going to use that module. Now we're going to create module mux 4-bit, and we're going to do all the same stuff, A, B, C, and Y in module. We need inputs, we need outputs, we need logic circuit. Now here's where it gets different. So now A and B and Y are all 4-bit signals. So we need to instantiate them that way. So we're going to say inputs. Now to do a multi-bit signal, I'm going to use square brackets, and I'm going to say for 4 bits, 3 to 0. What this does is it says it's going to create A3, A2, A1, A0. So if I did a input 1 to 0, that would be a 2-bit signal. 2 to 0 would be a 3-bit signal, and 3 to 0 is a 4-bit signal. If I wanted to make a 64-bit signal, I would have 63 down to 0. So input 3 to 0, A. Input 3 to 0, B. Now remember our control input is still just C. So in fact now let's kind of make a distinction here. Data inputs, control inputs, input C since that's just 1 bit. And then we'll have an output, which is also 4 bits, 3 to 0 for Y. Okay, let's see. Oh, because I'm done, and it should be mux 2-to-1.v. Good catch, Ethan. Why would you include the file in the file you're writing? All right, so here's where it gets weird. Now we want to create 4 separate instances of our mux 2-to-1 module. Like I said, if you've ever done any object-oriented programming, this is going to look a lot like that. So we define what module we want to use, in this case, mux 2-to-1, and then we give it a name. I'm going to call this one U3. By convention, U is a pretty common identifier for a Verilog module. U3, and then now we've got to do this. We're going to do A3. So we're going to grab the 3rd signal, or the 3 index of A, or the 4th one, the leftmost bit, A3, and you got to make sure a couple things. There's a couple ways to do it. One, you can look over at your module, and just like in a regular programming language, make sure the parameters are all in the same order. So that A3, B3, C, since C is just C, and then Y3. just like that. Another way to do it, I'll do it on the next line, mux 2 to 1, we'll call it U2, is you can specify which one you want to connect to. So if I wanted to do it out of order, but I wanted to specify, I could say something like this. I could say dot B, and in parentheses there, attach that to B2. And then say dot A, and in parentheses say that's A2. And dot C is attached to C. It gets kind of confusing when they're named the same thing. I missed closing parentheses. And dot Y is attached to Y2. So don't get too freaked out about this. Like I said, this is just two ways to go about doing it in the same order. If you are paying attention to the order in which your parameters are given, then you can just lay them down directly. But if you're not sure, you can specify, I want this parameter attached to this signal in our module. So you do that if you weren't sure, if you had them out of order. But I'm going to go ahead actually and just comment that out. And I'm going to copy and paste this guy down. And we'll go 2, 1, 0. And we'll go to the A column. We'll go 2, 1, 0. B2, 1, 0. 2, 1, 0. Just like that. So there we go. Now we have, actually I'm just going to go ahead and delete that. 4 instances of our 2 to 1 multiplexer that we've used to make a 4-bit multiplexer. Notice there weren't any assignments or anything like that. It was all just like that. So now let's go ahead and test bench it. Mux 4-bit underscore TB dot V. So timescale 1 nanosecond. 1 nanosecond. Let me go ahead and bring this over here so you guys can still see that. Include mux 4-bit. Here's where we include mux 4-bit.v module mux 4-bit underscore TB in module inputs outputs unit under test simulation. And now we're going to differentiate data inputs, control inputs. So reg. So here, same deal. 3 to 0. A. Reg. 3 to 0. B. We have a control input. Reg. C. And output wire 3 to 0. Y. And a unit under test. Mux 4-bit UUT A B C Y. And notice, so when we create our unit under test module in our test bench, we're actually just doing the exact same thing as we did over here in this module. We're just creating an instance of that module, and we're going to sort of put it through its paces and do some stuff. So initial begin and end. Now for a multi-bit module, it gets kind of weird. You don't necessarily want to test exhaustively unless you really know what you're doing. So what we're going to do instead is we're just going to throw some values. We're going to say, let's set A equal to 4-bit decimal, let's make it 12. And we'll say B is equal to 4D6, just like that. And let's delay for 10. Yep, sure do. Ethan's on point with those syntax checks. All right. So now let's go ahead and do this. I'm going to set C equal to 0. I'm going to delay for 20. C equal to 1. Delay for 20. And then I'll set C back to 0. and delay for 20. And then we'll call it finished. So what I'm doing here is just saying, well, let me put some values in A and B, and then let me toggle my control input to see what we should see is the value being passed back and forth to Y. So dump file mux 4-bit dot vcd dump vars 0 mux 4-bit tb. All right, and now we're ready to run. Look at that. I don't even need a syntax checker. Just have you guys here all the time. All right, let's see. So let's do it. Verilog option O mux 4bit.vvp mux 4bit underscore tb.v, and let's see what happens. Look at that, no errors, all is well. Mux 4bit.vvp. We got our file gtk wave mux 4bit.vcd. And let's see what we're working with. So there's a couple of things that we're going to see here that are sort of interesting and worth looking at. All right. So the first thing you ought to notice is this red wire that appeared here. Remember last time I said like red is bad. Red means things are broken. Here red means that it's undefined. In our test bench, look that we left C undefined, right? We set A and B, right? That happened right off the bat in the beginning. But we waited for 10 nanoseconds before we actually put a value into C. So here, C is X for it. We don't know what it is until we hit 10 nanoseconds, and then C went to 0, and then stuff started behaving properly. And now we can see here that A has the value C in it, and B has the value 6. C is equal to 0, so Y should be whatever A is. That's C, so that's good. And then it goes to 1. Now we can see that when C is equal to 1, the 6 is being passed to Y. And then we go back to 0, and we say, all right, so C is being passed back to Y. So we know our multiplexer is working properly. Now, like I said, you might notice that C is given here, or excuse me, the value of A is given in C. By default, Verilog, or excuse me, GTK Wave will show you values. When everything is a multi-bit value, it will wrap everything up as 1 and just show you what the value is. So for example, if I were to double click on here, now I could actually see the individual bits of A. I can see A3, A2, A1, A0, right? And we set it equal to 12, so that's 110. So that's exactly what we see here. But for convenience, it just says, hey, I'm going to wrap these guys all up for you and just say that the bus is equal to the value of C. Now, if you don't want to work in hexadecimal, you can right-click, go to data format, and you can pick all kinds of crazy stuff, right? If you're working with ASCII, you could set it to ASCII. Let's say we could set it to decimal, right? And now I can see that there's a 12 there, like we had set. I could set it to binary. Now I can see my 110. So you're allowed to sort of mess with it and get whatever sort of value that you want to work with, right? If you're comfy just working in decimal, you can also do this all at once. So I can right-click or shift select everything, right-click, data format decimal. Now you can see everything is switched over to decimal. So there you go. When you're making a multiplexer, that's all you really want to do. You just want to make sure that, you know, you don't need to test exhaustively, but you know, you just want to make sure everything is getting passed back and forth, and that all is well. So, any questions about how to create that multiplexer? Let me close this. You know, we started by creating a 2-to-1 multiplexer. We tested that, and then we created a 4-bit multiplexer that used our 2-to-1 4 times. And yeah, then we tested that, and all was good. Any questions about any of that stuff? We've got about 5 minutes left, and so I'm going to show just a couple of tricks. With 4 bits, it was pretty easy to make this work. But it's not hard to see that if you got to a large number of bits, 8 bits, 16 bits, 32 bits, 64 bits, this could get kind of tedious. And there are aspects of Verilog that are tedious, and you got to do a lot of boilerplate stuff that isn't that great. But one thing you can use to make life just a little bit easier is create what's called a generator. So I'm going to do this instead. I'm going to go and comment this part out, just so we still have it, but I'm not going to use it anymore. And we're going to create a generator loop. So the first thing I need is what's called a generator variable, or a genvar I. And then I'm going to create a generate block. So generate end generate. And basically what this does is it's going to go through and assign everything based on the value of I. So I'm going to put in here a for loop for I equals 3. We're still going to count down. So I'm going to say I equals 3, I greater than or equal to 0, and I minus minus to decrement begin and end. Now all I have to do is say this mux 2 to 1. I'm going to create just one thing here, u0. Then I'm going to say a sub I, bi, c, and yi, and put a semicolon on that. Now this is going to have, wrapping this in a for loop inside the generate block is going to have the exact same effect as this. But of course the obvious advantage is we can bump this up to whatever we want to be to create as many bits of multiplexing as we want. So let's go ahead and see if that works. I'm going to rerun our test bench to make sure we didn't screw anything up. Oh, look at that. Increment decrement operators require system Verilog. So it didn't work like my decrement operator, so I'm just going to do this. I equals I minus 1. Let's see if it likes that. Yep, it liked that. VVP. Take a look at our test bench, or our waveform. And yeah, we got the exact same operation as before. So that worked. So here, excuse me, the take-home message here is by using a generate block, we can save ourselves from having to copy and paste everything. Okay. So let's do one last thing. So let's put this in parentheses. I want to show you one last thing with our last 2 minutes. There's a much easier way to not have to do any of this. We can kind of cheat and make our signal behave. This is really going to look like a C style program. So I'm going to change my output here to a reg. I'm going to make it a register. This is a sequential logic construct. We'll see this again when we talk about sequential logic a lot. But for now, I'm just going to make it a reg. And then here, I'm going to do this. Always at star. Begin and end. Now, what this means is you will put, so this always at block triggers when whatever you put, whenever an input signal that you put in here changes. We'll see this when we do sequential logic a lot, and we'll see like things like pause edge, clock, and stuff like that. But here, always at star means when anytime any of the inputs change, execute this block. And so what we'll do here is we'll just say if C equals 0, then Y equals A. Else, come on, Y equals B. So that's probably much, much more like what you're used to seeing. And actually, I don't need this here. For just one-liners, it's all good. Yeah. Okay. So if you have just one line, you don't need to do the begin and end for everything. If you have multiple lines, then you need to do separate begin and ends for each guy. So begin and end, else, begin, and end. Again, in Verilog, think of begin and end as opening and closing curly braces. So, but again, if you just have one statement, and this is true in normal programming languages, like in C, you can do this as well, or in C++, you can do this without having to use curly braces. Let's run that one more time and see if that works. Yep, show does. And there we go, still a working multiplexer. So here's 3 separate ways to implement the exact same thing, right? The simplest, most obvious way is to use it is because Verilog apparently doesn't use the decrementer operator. Although it worked in that for loop in the test bench, so I'm really not sure why it didn't like it here, but it didn't like it for some reason. So yeah, so the traditional way of creating smaller combinational logic blocks and reusing them. Here we're using combinational logic blocks, but we're wrapping them in a generator. And here we're using a more sequential logic style, more C style block, but all of these implement the exact same thing. And also notice this one did not hinge on mux 2 to 1. So this one would operate, you'd only need to do this for your multiplexer. So, any questions about that? We are out of time. Yeah, maybe for Jinvar it doesn't like the decrementer, but I'm not sure. We'll dig, maybe someone can dig into that and figure it out for us. But anyway, there we go. That is everything that you need in order to do that project. And in fact, if you pay attention to this syntax right here, you can do that project pretty easily. So, but I will get that sort of tweaked and posted over the weekend. It'll probably do a week from Monday. And if there's nothing else, I see some folks typing.
Can you pull up the test bench for the mux bit 4?
Say that again?
Can you pull up this Verilog file test bench real quick? I don't have time right now.
Yeah, there you go. Yeah, Devin, your mic is rough. All right. So if there's nothing else, that is it. Have a good weekend, and I'll see you guys on Monday, where we're going to pick up on chapter 11. Start talking about sequential logic. And start talking about how to make memory. Dang, look at that. Reese is on point. All right.